Hi and welcome to Unit 2, Topic 2, Video 19. And in this video we're going to start looking at the modulus function. And you note that Unit 2, Topic 2, well, that's all about trig functions and trig identities. But we do have this little extra bit on the end. That's about modulus functions and reciprocal functions. We're going to talk about this now. There is certainly a direct relationship, but this is probably the part of it that's separated the most. And it actually relates to a lot of the work that you'll be doing or have done in math methods. So it does connect a lot of the topics. Learning goals, success criteria as usual. So let's have a talk about modulus functions. So the modulus function is defined as these symbols here. So we have vertical bars, which I've not drawn all that vertically, and they're around the x. So that is the modulus function. Now it means that if x is positive, then x is equal to x. So for any x greater than or equal to 0, x is equal to x. If x is negative, so for any x less than 0, then x is equal to negative x. Now that all sounds a little bit confusing, but what it's really saying, let's just talk about this verbally, is basically it just makes anything in that function set that's negative, turns it into a positive. It makes everything positive. And that's all the modulus function does. Now let's talk firstly about example 1, and I'll show you specifically what this means. So basically the absolute value, or the modulus of 6, is equal to 6. Whereas the absolute value, it's an absolute value is another name for it, of negative 10, well that's equal to 10 because it makes negative values into positives. So if you see those two vertical bars around the number in the modulus function kind of area, then we're talking about making negative things positive. Now I can see this could be a little bit tricky because if you see the vertical bars around a vector or around a complex number, well now we're talking about lengths, and we're talking about well, the modulus or the magnitude of a vector. So we've got some little problems there with the notation that we have to deal with, but you'll really clearly see where they apply. Determine the values of x such that, and now we've got two inequalities. So in a modulus inequality, we're looking at where the values lie. Now it could be just, from a dot or from a circle straight up or straight down, but it's usually between a few points. So let's have a look first at all. Determine the values of x such that 2x minus 5 is less than negative 1. So let's talk about definitions again. We know that the modulus of something, or the absolute value of something, makes it positive. So that means that this thing is always going to be greater than 0, which means that this can't be true. It can never be less than negative 1. So that is a false, and there is no solution. So it takes some time to think about that, but that's what's happening here. Now we've got the 3x plus 8 is less than 4. So basically for 3x plus 8 to be less than 4, we're looking for 3x plus 8 to be less than 4, or to be greater than negative 4. And then what makes that negative number positive, obviously if it's equal to negative 5, then it will become 5, which is not less than 4. So this is how we can deal with that modulus function, by taking it out and considering it as a double-sided inequality. Now I can do the same thing to both sides, but in this case I've got three sides. I'm going to subtract 8. That gives me negative 12 is less than 3x is less than negative 4. And then I can divide by 3. And that gives me x there. I get negative 4, and I get negative 4/3. So as long as x is between negative 4 and negative 4/3, then I've got a solution. And following what I've got over here in this blue bubble, I can create this solution graphically as well, which will give me this. I'll do a big nice long one there, and I'll pop 0 up here because I know what's about to come. And so if I pop 0 there and make this 2, this 4, so I've got negative 4, negative 2, negative 4/3 is about here. It is an open circle because it's less than but not equal to, and it goes between negative 4 and negative 4/3. So any value for x that lies in that boundary will satisfy this inequality. So let's talk about graphing modulus functions. So a modulus function when graphed basically takes any negative values and makes them positive. It's pretty easy really. I'm going to do this, but I'm going to flip across to Desmos to do this with you. So I'm here in Desmos, I've chosen to do this because if I sketch them myself, I can't guarantee it's going to be all that nice. But let's talk about the first example I had, which was the absolute value or the modulus of x squared minus 4. So what I'm going to do is I'm going to do x squared minus 4 just as a function. So you can see it there. I've not really set up the scale, but the effect will be the same. Now if I do y equals, and I use that vertical line bar, you'll see it over here. It's above my backstroke, below the backspace, but it'll be somewhere on your keyboard. And x squared, and then minus 4, and close that off. You can see all it's done there is it's taken those negative values, the values that are below the x-axis, flipped them up to make them positive. And that's all that's happened. Now I've got another example. So I'm just going to delete this guy here. My second example is the modulus of x all squared minus 3 the modulus of x. So this is a little bit different. So let's just start with x all squared minus 3 times x, except this time what's happening is we've got the modulus of x all squared minus 3 times the modulus of x. Okay, so what's happening this time is a little bit more interesting. So you can see we've got this modulus of x on the inside of the function. Instead of taking x squared minus 3x and doing the modulus of all of it, we're actually doing the modulus in the inside of the function. So we're actually creating something that's a bit of a reciprocal, but in this case around the y-axis, because we're doing the modulus on the inside. And so we can have a play with that and see how that looks right here. So I'm going to give you this example in a little bit more detail because it's a bit tricky to work with. This guy here that we've already done, well, it just made all those negative values positive. It just kind of created the line of reflection. It was like the function was sitting on a mirror. But in this case, it's a bit different. Because we're grabbing the modulus of x to start with, whenever we input a negative x value, it actually just looks at the y value. So you see this guy here, this is from the original function of y equals x squared, so y equals x squared minus 3x, the original function without the absolute values. It's taken those values and it's considering them as the positive x values, which means it's using these values down here. And that's why it's taking the values across to there instead of using the red values. So it's taking, instead of x equals, which -1 here, which is there, it's actually taking x equals 1, which is there, and printing that instead, because it's grabbing the absolute value of -1 and putting 1 into the function. And then it's doing the same thing at 2. So the value for 2 is right up here somewhere. But instead of using that value, it's using the value, well, that's the -2 value, so it's using the value for +2, which is there, and putting that in. And instead of using the value for 3, which is right up off our page, it's using the value for +3 instead of -3. So it's moving that value there. So it's actually just taking the y-axis and using that as a reflection. So you can see here that we get the reflection of the x-axis, if it's the modulus the whole way around, and we get a reflection across the y-axis that is the modulus of x inside of a function. So let's go back now and investigate the last two, C and D, on our Desmos page. So here's our Desmos page, and I'm going to go through and I'll just sketch, again, C, and then C in its original version. We'll C in its original version first, and then C in its modulated version. And so that is 2 cos x minus 1. Can't guarantee the scale's going to be great here, but that's not too bad. 2 cos x minus 1. Now you might want to just stop the video now and just take a second to think about what this might look like. It should take all the negative values and make them positive. So the absolute value of 2 cos x, I've just spelled that wrong, minus 1. And so you can see what's happened there. It's taken all those red values and flipped them up to make them positive values. Now I'm going to do the same thing with the last one. The last one you might remember was 2 to the power of x minus 1, but this time we've got the modulus of the inside, so the x. We get 2 to the power of the absolute value of x minus 1. And you can see again it's reflected now over the y-axis instead of the x-axis, because it's taking all those negative x values and treating them like they're a positive x value, and then creating that reflection. Now if you are sketching these functions, I strongly urge you to just take some time maybe to initially do tables of values to really think about what's going on, because table of values can really help. All the best.